So there are two ways you can look at it, right? If you're trying to ask what's necessary for life to exist, then you can say, where is there an energy source and what supplies the energy? That the Alvin explorers discovered is that there can be a whole ecosystem at the bottom of the ocean that lives off of electrons that never came. So in order to run life off of chemistry, you have to have something that's able to donate electrons to carbon. And the reason this happens on a geological planet like the Earth is that you have tectonic cycling. It's driven by heat in the interior that's trying to get up to the surface. This is what drives continental drift and moves the continents back and forth and gives us all of the shape that we know in the world today. But iron is heavier than oxygen and carbon are. And so as you get cycling, you drag down your iron more than you drag down some of the other metals. When the iron goes down, it leaves its electrons behind. When it comes back up at a spreading center in the middle of the ocean, it contacts water, and the oxygen and water can give those electrons back in the form of making rust. What that leaves behind is hydrogen, which has its own electron pairs, and those electron pairs have enough energy that they can drive chemistry. So one way to look at it, if you say, how can there be ecosystems at the bottom of the ocean living off of chemistry where there is no sunlight, you realize that the engine of the Earth's tectonic cycles is giving you things like hydrogen molecules, or sometimes the iron directly, that can donate electrons or electron pairs to chemical reactions. But then you can look at it in exactly the opposite way. Think about sparks or think about fractures in a material. There's no such thing as an immovable object. Anything, if you push it hard enough, will break. So if I take air, air doesn't conduct electricity, but if I force enough voltage across the air, I'll get a spark because it will find a way to make a path. If I take an elastic material, a sheet of metal or rock or whatever, and I flex it, it resists the flexing, but if I push hard enough, it will eventually break. There will be a fracture that propagates through, and that'll relieve the stress. Same basic idea in chemistry. On the early Earth, whether there was life or not, there is cycling that causes iron to get electrons from ocean water and leave behind sources of electron donors. If there's not life, those electron donors pile up, and you get something that's a little bit like the pileup of a voltage, except that in this case it's not a battery voltage between metal posts, it's a chemical voltage of a kind. It's called an oxidation reduction potential that says that you have an excess of molecules that are willing to donate electron pairs relative to other molecules that will take them. If you think of that as a kind of a stress on chemistry in a lifeless world, then the emergence of life provides a relief route for those electron pairs to flow. So now if you ask, is it believable that the emergence of life on Earth was a necessary part of the history of the planet's formation? You can say, well, in a planetary history without life, this stress would have built up and built up. Something had to give. So our guess is that the right way to look at the emergence of life is that this was the lightning strike, this was the spark through the graph of chemistry that was forced into existence by the accumulation of these chemical pressures.